Well, it's great to be speaking to this wonderful group. I'm glad to be giving this is my first talk of 2024, and it's on a topic that I haven't given a talk on before today. So please bear with me. I might be it might be a little rougher, but it is at least something that I'm enthusiastic about. Okay. So I'm speaking to a group of folks who study pangenomics, so I probably don't even need to motivate it, but I will give just a few slides worth of the typical motivation that I would give for pangenomics. And as somebody who wants to use pangenome indexes in order to analyze sequencing data and align reads, my main motivation is that pangenomes are one of our prime methods for avoiding reference bias. So the kind of bias that creeps into our genomic analyses when the reference sequence has reference alleles, but our donor sequence has some non-reference alleles, some alt alleles. And this can become a major confounder. This can become a major confounder if you're studying, for example, allele-specific anything. So allele-specific expression, for example, on this slide. It can become a major confounder if you're interested in regions of the genome that might be hypervariable. So any given donor might have very little resemblance to a given reference sequence, and therefore reference bias is more accentuated. It's also accentuated when the reference might be different from the donor in terms of being two different inbred strains, which can lead to spurious signals. In this particular case, the signal even sort of switches direction depending on which inbred strain you choose to use as the reference. So reference bias is the chief reason why we are approaching pangenomics. We would like for read alignment to be something that does not work better for some genetic groupings than for others, right? It should be a unbiased or as unbiased as we can possibly be procedure, regardless of the genetics of the donor individual. Okay, so this is our motivation, and of course, the good news is that there are now many years of wonderful work coming from the genomics community as well as the computer science community addressing pangenomics, and going back a fairly long way. One of the very first conferences I went to was the Genome Informatics in Cold Spring Harbor back around the time of this original Genome Mapper paper. And so I remember seeing the author of the Genome Mapper paper present that pangenome work. That was in the context of Arabidopsis, building a graph over many Arabidopsis strains. And of course, and this is a very incomplete slide, so I have to apologize because I'm sure there are people here who wish I had included one or two other things on this slide, but this is just a sort of representation of some pangenome indexing methods that have been proposed in recent years. What I want to relate this timeline to is another timeline that goes back a bit farther, which is the timeline of Burroughs-Wheeler-based methods that have been proposed over the years, going back perhaps, it could go back even further to the initial conception of the Burroughs-Wheeler transform, which I think some people date all the way back to the 1970s. But I started at the FM index, which appeared in the Fox conference in 2000. And on the Burroughs-Wheeler transform side of things, we've had many advances and breakthroughs, and many of them have had the effect of making the Burroughs-Wheeler transform more effective as a compressed index, and therefore as an index that we can use in the context of pangenomics. And so I'm going to talk a little bit about, because the move structure is in some sense just a bit further along this timeline, a relatively recent contribution along this timeline, but it is firmly in the Burroughs-Wheeler transform tradition. And as you'll see, the move structure really is just another way kind of building a compressed index over the Burroughs-Wheeler transform, and it bears a relationship to several other things on this slide. I think the one representative on this list that I think is particularly notable is the RLFM, which was published in 2005 by Veli McKeenan and Gonzalo Navarro, and it is probably, even since it's even earlier than the Genome Mapper paper, you might consider it to be one of the field's first steps toward pangenome representations. Okay, so I need to now talk about the Burroughs-Wheeler transform because the move structure is going to end up being an index for the Burroughs-Wheeler transform. And so I'm going to give a brief review and overview of Burrows-Wheeler transform so that we can make our way to understanding move structure. So the very simple way of saying what the Burrows-Wheeler transform is if you give it a string, and the string might be a genome, the string might even be a collection of genomes, might be many human genomes, for example, concatenated together. But at any rate, if you give the Burrows-Wheeler transform a string, it simply gives you a new string, which is a permutation of the original string. It permutes the letters, it puts them in a different order. And in particular, it reorders the letters according to the alphabetical order of their right contexts with respect to the original string. This picture doesn't really represent the context very effectively, so we usually use a different picture whereby we assemble a matrix, the Burrows-Wheeler matrix of all the rotations of a text T, and then we take the final column of that matrix, and that essentially operationally gives us what the definition says, a reordering of the letters of T according to the alphabetical order of their right contexts. Okay, so this is the Burrows-Wheeler transform, plus a few other things, plus a few auxiliary data structures, let's say, forms the basis of popular tools that have been used, like Bowtie and BWA, to analyze genomic sequencing data. Okay, so this is sort of how the Burrows-Wheeler transform started to creep into the way we do read alignment. The Burrows-Wheeler transform was originally developed actually for compression. And the action of the effect of the Burrows-Wheeler transform that makes it useful for compression is the fact that when we apply this permutation, when we bring the letters together in this new order, according to the alphabetical order of their right contexts, it means that like characters, so characters that have similar right contexts, come together. And when characters with the same right context come together, we tend to get runs, which is to say consecutive characters, consecutive stretches of the same character repeated, like these R's here in this bottom example. And the more repetitive the input is, right, I'm showing 3 examples that in some sense look like they're progressively more repetitive as we go down. The more repetitive the inputs are, the more, I'm going to use the term runny, the outputs are. So the outputs tend to have longer runs, fewer runs, and longer runs. Okay, so this is another relevant action that the Burrows-Wheeler transform has, right? Not only is the Burrows-Wheeler transform, when it is augmented with some other data structures, useful as an index, but it's also useful as a way of obtaining a compressed representation of the input. The way the indexes based on the Burrows-Wheeler transform work is essentially through a couple of different kinds of queries, a couple of different kinds of mechanisms. I won't walk through this example in a painstaking way, but I will say briefly that when we use the Burrows-Wheeler transform, or the something like the FM index, which is the Burrows-Wheeler transform plus auxiliary data structures, to answer a pattern matching query, we do a sequence of matching steps wherein we match longer and longer suffixes of our pattern. A way to think of it in terms of this matrix that's depicted is, in each step, we're finding the range of elements of the matrix whose prefix is equal to a suffix of our query, and we're growing that suffix in each step. And then perhaps when we're finished, when we have found the elements of the matrix that have our entire query as a prefix, we might then be interested in figuring out where they occurred with respect to T. If we're solving an exact matching problem, it's usually not enough to just know how many times something occurred. We'd like to know where those occurrences are. And so there's another kind of query called a locate query that we could use in this example to figure out that offsets 0 and 3 are the ones that had these 2 matches. And so I'm, roughly speaking, going to take the world of the kinds of queries that we pose to Burrows-Wheeler based indexes and divide them into these 2 categories. Match queries, whereby we match longer and longer suffixes of our pattern. We progressively find longer and longer, or we progressively find a narrower and narrower range of rows of the Burrows-Wheeler matrix that have a suffix of our pattern as a prefix, versus locate queries, which are about figuring out what once we do find the matches, what offsets did they occur at with respect to t? Okay, so roughly, and I'm gonna, this is the, I will refine this later. This is a rather blunt version of the idea, but roughly speaking, these queries, especially the matching queries, are based on something called the LF mapping, which is to say, if you find a particular letter in the L column that has a particular subscript, and in this case, the subscripts are just in ascending order as we go down the last column. If you find a particular letter with a particular subscript, then its LF mapping takes you to the row that begins with that same letter, with that same suffix. Sorry, I meant to say subscript, that same letter with that same subscript. So for example, here, the first character in our L column is this A with subscript 0. So the LF mapping had better take me to this A, right? The A of subscript 0. And so I would put a 1 in this first element of the LF mapping column. Likewise, for this B with subscript 0, I needed to take me to the row that begins with the B of subscript 0. That's row 5. So I would put 5 in for the next one, etc. So very roughly speaking, and this is an approximation so as to be able to get to the gist of the move structure, roughly speaking, all these Burroughs-Wheeler-based indexes, their job is to compute this LF mapping efficiently, including we might need to do it repeatedly, right? We might need to find the LF mapping, which takes us from one row to another row, and then from that row, we might then need to find an LF mapping, takes us to a new row, et cetera, et cetera. So at the core of the data structure is this functionality. It has to be able to do LF. It might have to do LF repeatedly. In fact, it usually does have to do LF repeatedly. Okay, I'm being a little rough and vague here. It turns out that real world queries do a little bit more than this, right? Like there are actually variations on the LF mapping. There are other sorts of adjustments we may have to do now and then. But it is fair to say that at the core of every important matching algorithm that uses the BWT is this LF mapping. And one thing to notice about LF before we move on is that it's a permutation, right? All it's doing is, it's taking a row to another row, but it's essentially just a permutation of the rows. So it's a permutation of the I column here. Okay, so in some sense, Burroughs-Wheeler indexes are a way of representing and querying a permutation. Okay, so over time, I mentioned before that as we index more and more repetitive texts, we end up with fewer runs and longer runs in the Burroughs-Wheeler transformed version of the text. And the field recognized early on that it would be awfully good if our BWT-based index data structures didn't have to grow like the length of the input. If instead they could grow like the number of runs in the output, that would potentially put us in a much better position to index repetitive texts. And so there was an ongoing quest in the theory community over many years to try to develop essentially enhancements of the FM index that allowed it to answer the same queries as a typical FM index, but while occupying a space footprint that grows like R instead of growing like N. N is just the total length of the input, whereas R is the number of runs in the Burroughs-Wheeler transformed output. And the progress happened in these two steps. The first step was the one I highlighted on the earlier slide, which was the McKeenan and Navarro RLFM index, which found a way to answer match queries, which is to say what the theory community might also call count queries, in roughly big O of R space, right? So in other words, the data structures that you could use to represent the index only required something like R machine words, or the constant times R machine words worth of space. But at the time, it was not known how to additionally solve the locate queries in big O of R space. So the locate queries were still stuck in the old regime of big O of N space. And it was a sort of ongoing open problem to try to develop an index that could do both. That could answer both the match and the locate queries in big O of R space. Many years went by. eventually in 2018, there was a solution, R-index, which was published in SOTA, which did achieve both big O of R space. It achieved big O of R space for both the match and the locate queries. And so this was a recent advance that gave a lot of hope to the theoreticians who worked on it, that we in the genomics community should perhaps, start working more closely with them and start adapting these data structures to work for pangenomes. I'll state, I'm about to move to the next slide, but before I do, I should just state the bounds on this slide are not 100% accurate. These are simplified, and I will come back to a couple of these bounds and give them the additional detail that's required when I talk about the move structure a little bit later. So folks like Travis Gagey and others who are part of the effort to develop the R-index data structure got in touch with people in the genomics community, including me, and we worked together to show that if you use the R-index, a major problem was how to build the R-index, which they additionally had to solve, which they solved using a method called prefix-free parsing. And then once it was practical to build, we could build it over collections of human genomes. And what we found was exactly what we would have expected and hoped, which is that because collections of human genomes are so repetitive, right? Two unrelated humans have incredibly similar genome sequences, 99 point something percent similar genome sequences. Because humans have such similar genomes, when we accumulate more and more genomes in an R-index, although the amount of sequence being indexed is going up, linearly with the number of genomes that we're adding, the number of runs in the Burrows-Wheeler transform of all those genomes is going up very sublinearly, definitely not linearly and much, much slower than what you see in the N column. So the fact that we can still answer our favorite sort of FM index-like queries, match and locate, and the fact that, but that nonetheless, the way that the index's space grows with the number of input genomes is much slower than N is very positive. It was a very good sign that the R-index could be a useful substrate for building pangenome indexes. And so just to be I'm repeating myself, but just to be clear, the input to the R-index could just be a collection of human genomes that are concatenated together, right? Like it really is, it's still a string-based method. It's not operating on a graph. It's not operating on a multiple alignment. It's just operating on strings. And so if you give it a collection of human genomes, they could be combined with something as simple as concatenating them. The R-index can build an index over that entire collection. And as the collection grows, the index will grow like R, the number of runs in the Burrows-Wheeler transform. And so this insight spurred more work, and these are just a few examples of work that came from a combination of Christina Boucher's lab, Travis Gagey's lab, and my lab to adapt the R-index to different settings, including sequence classification, especially sequence classification in the context of adaptive sampling for nanopore sequencing. Okay, so that's sort of a story about how the field got to the point where the Burrows-Wheeler transform seems to be a useful thing for pangenome indexing. I mean, indeed, it is a useful thing. It certainly is a useful thing for pangenome indexing. So if all this is true, then why look elsewhere? Like, why look to the move structure? Well, I think we actually can, and the move structure paper has its own, this is the move structure paper. This was published in iCalp 2021 by Takaki Nishimoto and Yasuo Tabe. And they have their own critique of the R-index, which is what they're trying to address in their paper. And their chief critique is that if you look at the actual bounds, I gave you simplified bounds earlier, but if you look at the actual time and space bounds, such that in which the R-index can perform match queries, there's actually a trade. You can trade one way or the other. You can either have a match query that operates in time that's linear, exactly linear in the length of the query. That's the first choice here, but not quite big O of R on the space side, right? On the space side, there's an additive log of n term, log of n over r term. Or you can trade the other way. You can have your exactly big O of R space, but now you've traded on the time side. you have something like a log of n over r term that's been included over on the time bound. So you sort of can't have best of both worlds of big O of m time big O of r space. So their critique was, we should be able to have both of these at the same time. Let's come up with a structure that achieves that, which they did. So that's their critique. We actually had a different critique, which is the reason why we were more excited about the move structure, which is the fact that if you look at the R index, it's complicated, right? It's a complicated data structure that has lots of components. So like this figure here is sort of like if you were to zoom in and then zoom in again on what's going on in the R index data structure, well, at a very high level, it has its data structures that are used to answer the match queries or the count queries. This is actually what I called the match query earlier. So maybe I'll just write match in there. It's got its data structures that it uses to answer the match queries. It's got its separate data structures it uses to answer the locate queries. And if you take one of those data structures, right, the one, for example, that enables rank queries with respect to the compressed, this one shouldn't be here, that was a mistake. Rank queries with respect to the run length compressed Burroughs-Wheeler transform string, well, it in turn consists of components. And one of those components might be, for example, a wavelet tree. And so, okay, well, this is a wavelet tree. Well, the wavelet tree in turn is composed of many components, and those components are bit vectors. And so that might look like this. And one of those bit vectors is something on which we need to be able to conduct rank queries, for example, or perhaps also select queries or other kinds of queries. In which case we need an index data structure over that bit vector that allows us to perform those queries. And so there's yet another level of complexity. And the complexity per se is not necessarily a problem, but what is a problem is that if you go to conduct a query, you have to touch all these data structures, right? Like you have to do a lookup here, and that tells you where to look something up there, and that tells you where to look something up there. These are all dependent, or many of them form chains of dependent memory accesses. And this means that you have poor locality of reference, right? In other words, doing one atomic sort of query, like maybe a match query with respect to the R index, actually requires looking at many disparate data structures, and it's going to incur many cache misses, which makes it slow, right? In other words, it's not a very good match to modern memory hierarchies to have a data structure that's this spread out over many, many components, large components. So that was our critique, and that's what made us sort of interested in looking at the move structure. Okay, so I'm about to explain the move structure. That'll be the most technical part of today. But just to return to this notion of the LF mapping and the LF mapping via permutation, for today, I'm going to assume that the LF mapping is really all we need. So in other words, as long as our data structure is capable of resolving LF mapping queries, you give me I, I'll tell you LF of I. As long as our data structure is capable of resolving those queries, I'm going to say it's good enough as a pangenome index. The reality is a little more complicated because tools use backward search, or they use ammonia-like algorithm to find matching statistics, and those add a little bit to the LF mapping queries. But the reality is all these methods are mostly based on LF mapping. And so I'm going to use that to justify the fact that I'm only going to explain how the LF mapping query works in the move structure. Okay, so on to the move structure. So let me use a bigger example this time, because if you want to talk about indexes that are compressed indexes, you need a very repetitive example for anything to be at all interesting. So I'm going to use this example here, row, row, row your boat 3 times. So just imagine these are, the input text T is just these concatenated. And so if we were to take the Burroughs-Wheeler transform of that repetitive input text, we would get something that looks like this. And as expected, it has long runs. Right? This is a known property of the BWT. This is why it's useful for compression, is because it tends to bring like characters together into runs. So you might say that when the input is repetitive, the Burroughs-Wheeler transform is runny, and this is my term. This is not a technical term. But likewise, the LF mapping is also runny. So when the input is repetitive, the LF mapping itself is runny in a sense. So for example, if we just highlight the R's in this diagram, all right, So we've got what I've got here is the last column of the Burrows-Wheeler matrix and the first column of the Burrows-Wheeler matrix, and I just turn them like this on their side. So it's like the previous diagram, but I turned it on its side. And I've highlighted the R's, and you can see there's two separate stretches, two separate runs of R's in the L column. And they come together into just one run of R's in the F column. But interestingly, they have, the way that they map is this kind of blocky way, where if you take those first three R's, the way they map is to the first three R's in the F column. And if you take the next chunk of R's, the way they map is to the next chunk of R's in the F column. So in a way, when the text is repetitive like this, the LF is operating at this kind of block level, right? It's taking sort of entire blocks of the L column and mapping them to the F column. And this statement here is just saying if you have two characters that are in the same run, like two R's that are in this run, for example, next to each other, then the way the LF mapping is going to map them onto the F column is in parallel, right? They're going to move in a parallel fashion. So if they were next to each other to begin with, they're still going to be next to each other after the LF mapping. And so this kind of parallel mapping we could actually visualize with parallelograms. So now I've replaced all those little arrows with two parallelograms because you can think of those as the two blocks of R's moving from L to F. And indeed, we can just draw all the parallelograms. It starts to look a little chaotic, but still, it's basically understandable, I hope, this diagram. And this is all the permutations, right? So like this is the whole permutation represented, but with this collection of parallelograms. And there are exactly R parallelograms, one per run in the L column. So the Move structure is a specialty data structure. It really specializes in representing and applying permutations that look like this. So I'm calling them runny permutations, right? Permutations that consist of relatively few and relatively wide parallelograms like this. And in contrast to R-index, it is able to operate in big O of R space and for one query, for one step of the matching process, constant query time. This is not a property that the R-index has. R-index has that trade. You have to trade away either on the space side or on the time side. There is an asterisk, and I said caveat coming later, because the version of the LF mapping query that's being solved by the Move structure has is slightly different than the R-index, and I'll say why later. Okay, now to explain how it works, and I'm going to move expeditiously, but hopefully not too quickly. So let's say we have our L and our F's as the last and the first column of the Burrows-Wheeler matrix. I'm going to use two bit vectors, which I'll call P and Q, to represent basically where the parallelograms start. Essentially where the left-hand sides of the parallelograms are incident on the two strings, right? So in other words, for L, that means I'm going to have a bit vector that marks the first letter of every run with a 1, and every other letter gets a 0. And then if I think of the parallelograms again, I think of how those ones move through the permutation, right? In other words, the one kind of like follows the left-hand edge of a parallelogram. I'm going to set the corresponding bit in the Q bit vector. So you can think about the parallelograms. Essentially, the way the parallelogram hits P and Q, you mark the beginning of it with a 1 on both sides. So we have our two bit vectors now, P and Q. The number of set bits in P and Q is both R, the number of runs in the Burrows-Wheeler transform. Okay. I'm not going to use the term LF for a while because, again, the Move structure is really just sort of, in some sense, a generic structure for any permutation. So I'm just going to call it pi for permutation. And so, for example, the parallelogram that I have depicted here is just representing these three components of the permutation that say that the permutation maps 46, 47, 48 to 13, 14, 15. What is the Move structure? The Move structure is a table. It's just a table. And the table is an array of records, right? Each row of this table is a record. And there's one record per what I'm going to call P run. So like a 1 followed by several zeros in the p bit vector, which is the same thing as a run in the Burrows-Wheeler transform. So the structure is just an array of records, 1 per run. Each record consists of these 4 things. One is the run's offset with respect to the beginning of the Burrows-Wheeler transform. I'm going to call that P. Another is the length of the run, call that L. Another is something I'll call pi, which is just if you take the head of the run, right, the one that's marked with a 1 in the P bit vector, if you take the head of the run, the first element of the run, it is the permutation, right? In other words, it's just the answer. It's what you would get if you were to move along the parallelogram from the head of the run to the Q bit vector. And then this thing C is the ID, which is to say, of all the runs, which run is this? Using zero-based indexing. It's the ID of the P run that covers the offset pi of P. Okay, this is not very useful to look at as a definition, so I want to show visual examples. That's when I think this will sort of come together a little bit more clearly. So let's actually build a few rows of the move structure based on this particular P and Q, this particular example here. Okay, so let's start with the very first run in P. That's just this run right here, very simple run because it's only 1 character long. So this run, it starts at offset 0, so I put 0 here. It has length 1, so I put 1 here. Okay, so far so good. If you actually look at the parallelograms again, which I'm not going to bring back because they're a little too cluttering, but I'll just tell you that the parallelogram maps that all the way to offset 46. Okay, so the parallelogram, in other words, the permutation maps offset 0 in the L column to offset 46 in the F column. So that's what goes in the pi column of my move structure. And then what C is supposed to represent is which, if I go from here to here, just jump from offset 46 in Q and just immediately look at offset 46 with respect to P, which run am I in? And you know, indexed in run space, right? So I have to set, so I basically, let's just count how many runs come to the left in order to answer this question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C should have 12. Okay, so that's the first row. I can do something similar for the second row. I'm now looking at the second run. So this run right here, that run starts at offset 1 and has 3 characters. If I move it through the permutation, the head of those 3 characters, right, this one, maps to offset 34. That's this offset right here. Okay, and then if I take the head and I look up here and I ask which run is that, I get the answer 8. This is with zero-based indexing. So that's the run that has ID 8 opposite that set bit in Q. And so on. I can do this again for the third run. The third run is longer, so it has length 9, so I put 9 there. The head maps to 52. The element that's opposite the head, notice in this case that it's not a 1, right? It doesn't have to be a 1. So just because there's a 1 in the Q bit vector, the opposite digit in the P bit vector does not need to be a 1. But which run is it in? It's in run 13, and so on. So I can collect a table that looks like this, and that is the basic move structure. In a way that's already pretty profound, that the move structure is just a table, right? Again, it's nothing like the R index, which is this very hierarchical, disparate collection of pieces. The move structure is really just this one table that you see here. It's no more complicated than that. Okay, fine. It's a little bit more complicated than that, and I'll give a couple complications later, but it's basically this. So if that's the table, how does it do its job? Because its job is to compute permutations. So we need this table to do a good job of telling us pi of I for arbitrary I, right? It's actually stored the answer for particular i's, which is to say the i's that are at the run heads, but we want to ask it about arbitrary i's, arbitrary offsets, which might be in the middle of a run. And it needs to be able to do this, including for repeated permutations, right? We don't necessarily just want to do it once. We might want to do a movement, and then from there another movement, and then from there another movement. So we need to be able to support repetition. Okay, so let's look at a couple examples to see how difficult is this. Does this pose any problems? All right. Well, if I start with some offset k that I'm asking that I would like to permute, and let's say that I is the ID of the run that contains k. So in this particular example, k is right here. And because this is run 2, I drew the line a little too far. Because this is run 2, I'm going to say that k is 10 and I is 2. Then in order to update k, in order to get the permutation, in order to get my new offset after the permutation, I need to apply the permutation to the run head, right? So the head of the run that k is in, right? So that means I need to apply this permutation. This one goes to here. However, I started in the middle of the run, so I need to now adjust by adding on how far into the run k was, right? In this particular example, k was 6 digits into the run. So if the run head maps to offset 52, then k, which was 6 over from the run head, maps to offset 58. And so my new k should be 58. Okay, so that's essentially, again, using the parallelogram. That's like saying, if I'm in the middle of a parallelogram, if the left-hand side of the parallelogram got mapped to 52 and I'm 6 over from there, then I got mapped to 58. Okay, so that's fine, but if we'd like to apply this repeatedly, then it's not enough for me to update k. I also need to update I. I need to know what's the new run ID for the run that I'm in. In other words, what's the run ID here? Okay, so what we might hope is that this element, wherein we stored the run ID corresponding to the image of the head of the run, is the one I'm looking for. We might hope that. And this example, it actually is. So in this example, it works, right? That 13 that's been stored in the C column is the correct ID for the run that is opposite the location where k mapped. However, all I have to do is show you a somewhat different example. So in this case, yes, a somewhat different example, and you see that that's not always the case. So let's apply the permutation now where we've got k is 31, and this is in run with ID 7. We do our usual first step, which is to say we apply the permutation to the run head, and we ask how far we are from the run head. In this case, again, we are 6 away from the run head, and the run head maps to 37. So that means that this position maps to offset 43, right? This is offset 43 right here. Now I'd like to know, which run am I in? Which run is this 0 in? This one right here. Well, if I were to simply take the element that you see here, that would direct us to the 9th run. This is the 9th run. This is the run with ID 9, and that's not the correct one. I'm over a couple runs. I'm over here. And so 9 was not the correct answer. That run, the run with ID 9, only contains offsets 37 and 38, but I'm in 43. So I'm not done. I have to sort of keep walking. I have to sort of keep trying, sort of scan linearly forward in the move structure until, right, the rows are in order, right? Or the rows are in order by run. So I can just sort of scan forward on the table until I get to the table that happens to contain offset 43, and that happens to be row 11. So even though I went to row 9 first, that was not the correct row. I had to do some scanning to figure out where I really belonged, which was row 11. Okay, so good news, bad news. The good news is that this means that we can recover from this problem of the run ID not being exactly the one that the head mapped to. However, the way we recover involves a linear scan. And so what Nishimoto and Tabe had to establish is that this linear scan is not so bad, right? That the linear scan is okay. And so they had to argue, however we do this query, the worst case query time, of course, has to be inclusive of how many times we scan, right? The scan is work. So our worst case query time is inclusive of these scans. We'd like to be able to bound the amount of scanning we have to do. So this is the meat of Nishimoto and Tabe's paper, and I'm going to show you briefly what that proof, what that technique and proof is like. I'm actually going to follow the explanation from a different paper, this one by Brown, Giggy, and Rossi, because I think it's a little easier to follow. But I'll just get to the point where I can show you that we can put a constant bound per query on how many times we have to scan forward. And then that'll be the end of the technical portion. So the idea is, if this is our initial P and Q, our initial P and Q is defined entirely by the runs, right? By the runs of the BWT. Now we're going to modify P and Q from their original form. And specifically, we're just going to set more bits in P and Q in such a way as to split the runs into pieces, but in a very intentional way. So for example, if this is our P and Q, and we just imagine this parallelogram here, right? This LF mapping from this chunk to this chunk, we could split this initial run into two runs, right? We could just artificially say, yeah, you know what, never mind, I'm going to consider this to be two separate runs, in which case I should also split the image of that run, right? So down here, I should do another split here. So setting those two bits to one is essentially taking what used to be a run and turning it into two subruns that are exactly parallel to each other. They're adjacent and parallel. And that sort of takes the permutation where originally there was one parallelogram, just splits it into two. Right, but it does not change the permutation itself. It just changes our representation of the permutation, makes it a little bit bigger, but there might be a good reason to do this. So the idea is we're going to do this, we're going to split runs, we're going to keep doing it until we can guarantee that no permutation that takes us from a ki to a k prime I prime is going to require 2D or more fast forwards where D is a parameter we get to pick. It has to be at least 2, and it's a parameter that we get to pick. Okay, so how does this work? Well, consider the qubit vector and consider all the runs in the qubit vector. Right? The idea is that if you look at the stretch of the p-bit vector that's opposite a run in the qubit vector, we want there to be a known, bounded, constant number of ones there. Right? We want to put a bound on how many ones there are in that stretch of the p-bit vector. So if we consider each q run to have a weight that's equal to the number of ones in the opposite portion of p, and in this example, I've highlighted a run in q that has 3 as its weight, right? Because there's three ones up here in the p-bit vector, then the idea is we want to sort of knock down the weights of the highest weighted q runs until the guarantee holds. We want to keep attacking the highly weighted q runs until there is a guarantee. So we do a loop like this until all the q runs have a weight that's below 2D, right? That's the ultimate guarantee we want. We pick the q run that has maximal weight at the moment, right? If there's a tie, we pick arbitrarily. We then split it, which is to say we set a bit in q so that on the q side, we end up with two smaller runs, and we set the bit such that the first subrun has weight D and the other has weight at least D. So we sort of like chop off a weight D sized interval from the beginning of that run and make it its own subrun. So in this example here, if we were doing this, then we would want to set a bit here such that we end up with one run that has weight exactly 2, right? So now that's this run here. This run has weight exactly 2 because it corresponds to those 2 ones. And then another one that has weight at least D, right? So that other interval, that other sub run here has weight 4, right? So that one doesn't accept one doesn't adhere to the guarantee yet, but at least that first sub run now does adhere to the guarantee that we were looking for. It's not enough to set the bit in Q, we need to set the corresponding bit in P, right? There's a correspondence between P and Q that we're trying to represent. So if we set a bit in Q, we have to go through pi inverse and set the corresponding bit in P, and that allows us to do the splitting properly on both sides. And we simply iterate this until no Q run has weight exceeding our 2D limit, or reaching or exceeding our 2D limit. That's really all that's needed. So it is an iterative splitting procedure that takes our initial set of parallelograms, of which there exactly are, and it creates more parallelograms, creates more blocks, but there's actually a guarantee on how many additional blocks it's going to create, such that it can only be a constant times R blocks at the end of the day. right? So in other words, it's not proved here. It would take me too much time. It is proved in these papers. But the number of iterations, which is to say the number of new subruns that are created, can't exceed the number of set bits in the initial. So that's the same thing as R divided by D minus 1. So at the end of the day, it was big O of R to begin with. It's still big O of R after we apply this splitting procedure. But now we have a guarantee that is a constant time guarantee on each individual permutation query. That's the crux of the Nishimoto and Tabe result. Okay, I said before when I said big O of R space constant query time that there was an asterisk. The asterisk is this version of the LF mapping is not just going from index to index, like K to K prime. It's actually about two things. It's about going from a pair, which is an index and a run ID, to a new index and a new run ID. And that's different from what the LF mapping meant in the world of the R index and the world of the FM index. So in some sense, this combination of bounds was not for the most generic version of the LF mapping that you could imagine. It was for a specific version of the LF mapping where you are, in some sense, provided the initial value of I. If you are not provided the initial value of I, then you have to go compute it. And that computation could be a rank query, and that could be worse than constant time. And that would affect the real, the real big O time of your query. So under the assumption that you can be provided with the initial value of I, this statement is true. Okay, so to sum up what I would convey about the Move structure itself, I then have to get to the Movi software, which unfortunately I'm going to kind of rush through. But the data layout is incredibly simple. The data structure is a table. What you have to do in the course of a single match query, the single LF mapping, is you have to move to a new row, and you potentially have to move forward a little bit, but only a constant amount to find the row you really belong in, and then you repeat. So the inner loop requires one big movement through memory, right, which is the jump to the new row, the one that goes through the pi column. And then it requires potentially some scanning, but that scanning is sequential and bounded by a constant. So the layout is very simple. It is not a disparate collection of data structures, all of which you have to potentially touch to satisfy a query. It's one table, and you only have to make a move and a scan at each step. And the actual computation you're doing in the inner loop was no more complicated than the adds and the subtracts that I showed on the previous slide, right? Like there's no, if you crack open an FM index implementation, there's like population count and maybe you're doing prefetches and, none of that, right? The inner loop of the move structure is just addition, subtraction, lookup. So it's remarkably simple. And although I said that it's as simple as what I showed here, really the reality is a little bit more complicated, usually because you want to do queries that go a little bit beyond LF mapping. Like you might want to do backward search, or you might want to do a Moni-like matching statistics procedure. In that case, usually you can solve your problem by adding columns, right? In other words, as long as the new information that you're using to augment the data structure can be laid out parallel to the BWT runs, it can simply be added as a new column for the move structure. And this is something that we do in the Movi software. Okay, so a few words about the Movi software. This won't be very long, and so I guess what I'm really saying here is you should look at the preprint for more details. But because of the move structure and its properties, we were very eager to implement it. We wanted to see, we hypothesized that because of this wonderfully simple data layout and this wonderfully simple inner loop, that we could be a lot faster than the R-index-based structures that had come before for BWT-based pangenomes. I think I might kind of skip most of what's on this slide and actually just concentrate on what's inside the red box here, because this is a head-to-head comparison between a move structure-based pangenome, which is Movi, versus an R-index-based pangenome structure, which is R-index. And what you see is that Movi is bigger. This is perhaps not surprising, looking at that table that's full of, sort of dense, full-sized integers. right? The constant factor that's being multiplied by R is relatively large for the Movi structure. And so it does end up being bigger than its R index counterpart, but it is much faster, order of magnitude faster to do the queries compared to the R index based pangenome. You can look at cache misses directly, right? So we did this using CacheGrind, so a tool that lets you profile cache misses in an emulated environment. And as expected, the inner loop of Movi, and we're measuring here cache misses per base. So in some sense, this is cache misses per inner loop iteration. For Movi is close to 1, right? It's 1.57. For Spumoni, it's over 20, right? Again, emblematic of the fact that Spumoni uses the R index. R index has to touch many disparate data structures in each query. So this is not only efficient per inner loop iteration, it also sort of lives in a much more narrow band, right? If you just look at the box plot on the left, it's not only lower, but the whole span of the box plot is modest enough that you might also say that it leads to a very predictable inner loop, right? The inner loop does not have a huge range of time intervals that it might take. It's a relatively narrow band of time intervals, which can be useful in applications where time is of the essence. You have a time budget, for example, adaptive sampling. You have to make a decision within however much time is needed to send a prompt signal back to the nanopore. And then a final point is that although the constant factor is big, the big O of R scaling actually allows Movi to scale a bit better than competitors, especially Spumoni. You might wonder, why is that? If they're both big O of R, why does one scale better? And the answer is because Spumoni is not really big O of R. It has hidden under the rug the fact that there are some, like, for example, log n over R factors in there, right? And there are no such factors in Movi. Movi is very strictly and honestly big O of R. Okay, I think I'm going to skip that. So in terms of takeaways, I want to finish before the hour to be kind to everyone and to leave time for questions. BWT-based pangenomes are full text indexes. This is an important point I didn't emphasize too much. They're not K-mer-based, right? Like you can query any substring you want with a full text index. So BWT-based pangenomes are full text indexes. They provide the big O of R scaling that's needed for pangenomes, for the many genome future. And the Movi structure is a BWT-based index whose simple data layout and incredibly simple inner loop makes it really remarkably fast. Movi is an implementation of this idea. It achieves excellent speed, excellent space scaling, and the main expenses that we pay in terms of the constant factor that's in front of the R in the space usage relative to the R index, we seem to be a bit worse. It's the fastest compressed full index that I've ever heard of. I could be wrong, but an inner loop that operates at almost 1 cache miss per inner loop iteration is close to as good as you could even imagine getting with a full text index. And the predictability makes it particularly well suited to adaptive sampling, where speed and predictability are really the key. Okay, so with that, many thanks to lots of collaborators on Spumoni, Movi structure, and R index. And thank you for your time, and I'm happy to answer questions.
Thank you. Thank you very much, Ben. Are there some questions in the audience? No, it's... you can hear me, Ben?
Yes.
Okay, great. Okay, so maybe I'm going to start with a small technical question and more curiosity one. Yeah. I guess there are, well, maybe not in the case of pangenomes, but sometimes you are going to have very small runs, and maybe it's better to store them as usual, just LF instead of all the 4 integers of the full line. Are you considering this situation for gaining space?
Right. Yeah, I think that overall, the big O of R data structures, if there's a spectrum from things that are not compressible at all to human pangenomes at an extreme level of compressibility, then there's definitely a lot of interesting stuff that's intermediate, right? So like, in fact, I would say most of metagenomics kind of lives in this intermediate space where you're not, the genomes are not 99.8% similar. They're very different from that. And you end up with compression ratios using the big O of R-based data structures that are not so good. Sometimes they're good. I would say, for example, for 16 sRNA sequences and 18 sRNA sequences, you actually end up with very good N over R compression ratios. But in that middle space, I think that other methods that are also that are more like hybrids of FM index and R index are probably going to perform better. There's one recent preprint by Li Song at Dartmouth describing a tool called centrifuger, I think it's called. Anyway, but it is tuned for that intermediate space, like the kind of conservation you would get if you had all the genomes in a bacterial clade, for example. But this is a very good point, right? The compression ratio you get with big O of R-based data structures, it's usually there's a point at which it's not worth it, right? You should sort of go back to the FM index if the compression ratio is not so good. And there are some new methods that are doing better at that interface, but they're somewhat different than the ones I described.
Mm-hmm. Thank you. Some questions here?
Yeah, can I?
Yes, Alex.
Yes. So I maybe didn't really fully get the point, but if you would like to make savings in terms of the data structures you use, so is this the major point to not use two, you have two bit vector representations, succinct ones, allowing for rank select in particular here on P and Q, and then you have like the most efficient data structure you can imagine to implement kind of permutations, which is you have the two selects here and there, P and Q, and you have the permutation in between. Yeah, whatever there is possible. I don't remember exactly. But this is what you do not want to do that. Yeah, if you have these three data structures, you get everything you have, I think. Am I correct?
So the P and Q bit vectors were how I explained the building of the move structure, but the move structure doesn't include those. The move structure really is just like, for example, what's on this slide.
No. Sure. Mm-hmm.
So this is the move structure.
I mean, have these three data structures instead of yours, yeah? And why exactly are you using yours? Because you inherently or hiddenly implement permutations, right? One the other way, yeah?
You're asking why not simply use P and Q?
Why not
as the data structure
as big vectors and have some really nice implementation of permutations in between, yeah? That maps the ones in the P to the ones in the Q. Yeah. And you can query the ones and the P's and the Q's using select. And then you...
Well, I would say in a sense, that's what we did. That's what we did. And further, it allowed us to throw out P and Q, right? Like, in other words, the move structure is the representation of the permutation that goes from P and Q. And it so happened that it was full featured enough that we didn't need to keep P and Q around.
So this is the purpose. You would like to make savings on the number of data structures, and I'm very generous here. And you're not, yeah? Is this?
For sure. I mean, like, for example, the R index, it has advantages, right? So the R index contrast that I drew here, there's a reason to do it this way, even though this has many disparate data structures.
Yeah.
You can almost think of what it's doing as if you start from the move structure, but then you compress the move structure in a columnar way. Like if you look at each individual column and you think about what's the best way to compress it, you're ultimately going to then detach the columns from each other and apply all kinds of compression, and maybe you end up with wavelet trees and things like that. And it will look more like this. But the reason the move structure appealed to us is specifically because it reduced the number of structures to just one, which means that when we do pay that cost, there's an inevitable cost of at least one cache miss in the inner loop for a sufficiently large data structure. But once we pay that cost, we don't have to pay any additional cost, or very little additional cost.
Okay. Thank you. Thanks.
Thank you.
Bruna?
Hi. So I have a question about the 1.57 cache misses. So is it more than one because you have this sequential searching, or is it for some other reasons?
Probably not. I think it's chiefly because there's sort of a second case that I didn't describe. So when I reduced the problem to just the LF mapping, I had to explain that that was a rough approximation, and that really, if you're doing, for example, matching statistics queries, there's something else you have to do. We call it the repositioning step. So in the real Moni algorithm, each inner loop is not necessarily just one LF. It might be an LF plus a repositioning. Let me get to the slide you were talking about. So some inner loop iterations are just an LF, and other inner loop iterations are both an LF and a repositioning step. The repositioning step is sort of like tantalizingly, it's not very far. It's not a very large movement through the data structure. It is basically to one of the two nearby runs that have the desired character. And so you either go up or you go down, and you don't necessarily go very far, but it's far enough that it's likely to incur a cache miss. So I think that explains the 1.57 as opposed to 1.
Thank you.
I had another question personally. This is always the same question I ask to everyone, because when we talk about pangenomics, we would like to add some genomes. So
yeah,
use some dynamic data structures. I guess this one, as all the Burroughs-Wheeler ones are not dynamic, when you want to add a genome,
right.
You have to recompute everything from scratch.
Yeah. Yes, this lives in that awkward space of hard to dynamically update, I would say. And I'm not as familiar, like there is literature about dynamic updates to FM indexes, and I'm not so familiar with it, but I do think this is probably in the category of hard to update dynamically.
Okay. No way to merge two Movi data structures or two Move data structures?
Well, I don't come with any insights about exactly how to do it, and so I should probably say very little, but I would say that in some sense, if the two extremes of the problem shouldn't be hard, right? Like, so what I mean is if you're adding one more sequence that's essentially a clone of one of the sequences that are already there, then all you're doing is taking existing runs that are already there and making them longer. And so that case should be easy. I don't know how I'm not proposing that I know how to do it, but that case sort of should be easy. And then on the other extreme, if a sequence bears no relationship sequence-wise with anything else that was in the collection, then there's going to be a strong tendency for its runs to interleave with the runs that are already there without joining them, without making the existing runs any longer. You're going to get sort of like an interleaving of runs. And so in some sense, that shouldn't be so hard either. But the real thing that will happen is something in the middle where some runs get longer and some runs get introduced and interleaved into the existing ones. And of course, you can't avoid the full pain of having to figure out which case is which in all cases. So I do think it'll be hard in general.
Okay. Are there some other questions? Yeah. Remotely, do you have some questions? Okay, so if not, I would like to thank you again, Ben, for accepting to give this talk. It was very nice, very clear. And again, I wish you a very nice new year, and see you soon. Thank you.
Thank you. It was a pleasure. Thank you very much.
Goodbye.
Thank you. Awesome talk.